Okay, today in this video we are going to start with introduction to electromagnetism. So before that introduction to electromagnetism, we need to understand few mathematical notations and we need to understand few mathematical operators that will be frequently used in this particular topic. So to start with introduction to electromagnetism, let us first understand what is field. So or fields, I will say. So what do you mean by these fields or field? Okay, so we can define this actually. This field is a region or space in which every physical quantity can be expressed as a continuous function of the position in that region or space. So every physical quantity can be expressed as a continuous function of the position. Okay, so we will call this a field, right? So these fields can also be classified into two categories. You have already done this, and you classified the physical quantities into different types. And you said one is scalar quantity, the other is vector quantity. The same way, as I said, every physical quantity can be actually represented as a function of position. So accordingly, we can classify these fields into two types, and I will say scalar field and vector field. Okay, so if I will classify this field as scalar field, one is scalar field and the other is vector field, right? So now when I will say any scalar quantity is scalar physical quantity, that will be in this scalar field, and all other physical quantities which are vectors will be in vector field. So this way we can just define field as scalar and vector field, okay, depending upon the physical quantity which can be written as a function of position. Okay, so so all the quantities either in scalar field or in vector field are nothing but the function of position and time. So all these field, vector field or scalar field, we need to write these as function of position and time. In three dimension, I will write this as the position and this is the time. Okay, so everything, all these physical quantity can be represented as a function of position and time. Okay, after that, let us define few vector differential operators. So vector differential operators. Vector differential operators. Vector differential operators. So one vector differential operator that we will discuss is del operator. We will call it as del. The notation that we will use is a triangle in a reverse way and del. Okay, this is the symbol that is used. So del operator. Okay, let us talk about this del operator. So what is this del operator? Mathematically, actually, this is defined as or can be written as this del symbol I am writing. This is a triangle shape. You can see that mathematically it is given by I cap del by del x plus j cap del by del y plus k cap del by del z. As you all know, this I cap, j cap, k cap, these are all unit vectors in respective directions like x, y, and z respectively. I cap is unit vector along x direction, j cap is unit vector along y direction, and k cap is the unit vector along z direction. Del by del x, del by del y, del by del z, they denote the partial differentiation or derivative with respect to x, y, and z respectively. So we all know these notations that these are used. So del operator, sometime also we can call it as nabla operator. This is also known as nabla operator, right? So this del operator can be mathematically written this way. Del is nothing but I cap del by del x plus j cap del by del y, k cap del by del z. So I cap del by del x gives you actually what is the change in a particular scalar or a vector in this direction, in the x direction. Similarly, in the what is the change when it is operated in on any scalar or vector, what is the change in y direction. Similarly, what is the change in the z direction. So when I will operate this del on any function like any scalar or vector field, it will actually give us how that particular function, that particular physical quantity changes, right? With respect to this x, y, and z, or in x, y, and z direction. So that is what is the objective, and we are going to find out that. Okay, so after this, let me just tell you if what will happen if I will operate this del operator, okay, this del or nabla operator on a scalar, okay. So what we will get? So let us now discuss what is gradient of a scalar field. Okay, so let us see what is gradient of a scalar field. Gradient of a scalar field. So let us just see that gradient of a scalar field. So the vector that will represent, in magnitude and direction of the maximum space rate of increase of a scalar. Maximum space rate of increase of a scalar is known as the gradient of that scalar. So what do you mean by that? Let us make it more clearer. So if I will write, suppose a function, a scalar, I will write. I told you that a scalar field can be written as a function of position. So x, y, z, okay, these are the space coordinates in Cartesian system. We took phi equals to phi, sorry, phi function of x, y, z, okay, and this is our scalar function, right? And now if I will write what is the gradient of this scalar, okay, what do you mean by gradient of this scalar? I will write, you can symbolically write it as grad phi, that is nothing but del operator, okay, because that del only gives us the change of any function or any physical quantity in x direction, y direction, in z direction. So if the if the function changes, if the physical quantity changes in a particular region and space, then we need to see how it changes in the x direction, y direction, and z direction, and that can be determined by operating this del operator on that function. So I will write grad phi is nothing but this del phi I will write. So mathematically, if I will write this can be written as I cap del by del x plus j cap del by del y plus k cap del by del z. This is the mathematical representation of the del operator, and then whatever our phi value. So here normally I have just written it as phi, so I'm writing it as phi. Similarly, if a function will be given, then you can operate on that function, which we will do in some numerical calculations. I will show you how to do that. So here finally I can write I cap del phi by del x plus j cap, the second term, del phi by del y plus k cap del phi by del z. So if you want to write what is the gradient of this phi function, right, phi, which is a function of x, y, z, the space coordinates you can see, okay, then we can write it this way mathematically. So mathematically you can write this, okay. So if you want to find out what is the incremental change, or you can say what is the change in phi, okay, so in terms of differentiation, if I'll write d phi actually gives you the change or incremental change of the scalar function, okay. And if you want to write it mathematically, this d phi actually gives you what, this is the ordinary differentiation, and in terms of partial differentiation, if I want to convert it or write it, we know that d phi can be written as, because phi is a function of x, y, z, so we need to see how phi, this is just a unitary method. When you said phi is a function of x, y, z, actually how that phi varies along x, how phi varies along y, how phi varies along z, that is what we need to find out. So now I can write this as del phi by del x. This particular partial differentiation gives you what, how phi actually changes with respect to x. Then suppose dx is the change in x, then I will multiply del phi by del x into dx, so that will give you the overall change in x direction, right? Similarly, we can write it as del phi by del y for the y part, dy, if dy is the change or elemental change in y, is dy. Similarly, del phi by del z, so how phi varies with respect to z, Okay, and then what is the elemental change in the z, so we can write this way. So d phi, the overall change in phi depends upon x, y and z, the variation of phi in x and phi in y and phi in z, right? So del phi by del x gives you the relation between phi and x, how they actually, what is the rate of change of phi, and then dx is the change in x. Similarly, del phi by del y as a whole gives you what the rate of change of phi, how it actually varies with y, and then if dy is the change, same way the third term del phi by del z into dz, right? So this is how we can write. Okay. Further, this expression can be rewritten as, so what we got, I'm just rewriting it quickly. D phi equals to del phi by del x dx plus del phi by del y dy plus del phi by del z dz. This is what we got, which can further mathematically we can write this as del phi by del x. See how I'm writing, then I will explain you. J cap del phi by del y plus k cap del phi by del z. Okay, this is a vector, you can see that. Okay, you can see I cap del phi by del x, j cap del phi by del y plus k cap del phi. Sorry, there was a disturbance. We will continue from that. So we had, grad phi is this. Okay, let me just rewrite it again. I cap del phi by del x plus j cap del phi by del y plus k cap del phi by del z, right? And this is nothing but your what, if you I mean, if you remember, we wrote it for delphi, right? And then dot, I can write I cap dx plus j cap dy plus k cap dz. If you will see here, what it gives you, I cap dot I cap will exist, I cap dot j cap will not exist because dot product cos and the angle between them 90 degree, so cos 90 degree will be 0. So you can see only the components, I cap dot I cap here, j cap dot j cap here, and k cap dot k cap here will exist, or the terms will vanish. So this way we can write. So I can write this d phi as this. So the first term here, first this one, we wrote it as del phi. We said this is nothing but our grad phi or del phi, and dot this I cap dx, j cap dy, k cap dz. You can see, simply see, like it's just similar to I cap x plus j cap y plus k cap z. Only thing is, in place of x y z you can see dx dy dz. So that can be written as actually dr, the incremental change in the position vector, or the differential or the elemental position vector, right? Considering all the dx dy dz in x y and z directions. So we got d phi is equal to del phi dot dr, where this del phi is our gradient on a scalar. This del phi is the gradient of a scalar, right? So this is what we got. Okay. And okay, I just wrote this is your r vector, which is the position vector actually we said, and dr I wrote for I cap dx plus j cap dy plus k cap dz, right? So I hope you understood this. D phi equals to del phi dot dr. Now if some, okay, so this gives you what the incremental change in phi, so overall change in phi, where phi is a function, scalar function. Okay, that is a, that depends upon xyz, right? So if there is any variation in xyz, what will be the overall change in d phi? That is what we got. Now if you want to write few examples of gradient operation, we are aware of the electric field. So electric field is actually the negative gradient of potential, which can be written as minus del v. So in three dimension, this del operator gives you the meaning, right? How it changes in x, y, and z in all three directions. In one dimension, if you remember, you have written it as E is equal to minus dv by dx, right? In this form you can write. Okay, in three dimension you can write it in the form of, this del operator. The same way we can write it for gravitational field at a point. So if you want to write gravitational field at a point, can also be written as minus this gradient of the potential, which is function of gravitational potential, which is also function of r. Right here, electric potential, which is function of r. Okay, electric potential we know can be determined from the Coulomb's force, and here gravitational potential can be determined from Newton's law of gravitation. Okay, F equals to gm on m2 by r square. Here you can, from the electric or say Coulomb's force, you can write F equals to k times q1 q2 by r square. From that you can determine. So this is how, these are the, two basic examples of, this operation of gradient, how this gradient vector in three dimension actually works. Okay, so once this is done, we can now move to what is the physical significance of gradient, that we need to find out. Physical significance of gradient. Physical significance of gradient. Physical significance of gradient. Now physical significance of gradient, if you want to see, so the relation that we just now derived is given by d phi is equal to grad phi dot dr. Okay, so d phi, you can see dot product, that's why this part is a scalar quantity. D phi gives you the overall or incremental change in phi. Del phi is the vector, because it's the del operator operating on phi. So this is a vector given by I cap del phi by del x, j cap del phi by del y, k cap del phi by del z. So all unit vectors are associated, so you know that this is a vector. Dr, I cap dx, j cap dy plus k cap dz, this is also vector quantity, right? So what is d phi? D phi is the change in the scalar function due to the change this. This is the change dr. This is the change in the space coordinates, right? So because of that, you got the change in the scalar function. So if there is a change from r to dr, that is r plus dr, then the change in the scalar function will be phi plus d phi. So for a dr change in the space coordinate, you got a change in the scalar function as d phi, right? Mathematically further, if you want, we can just rewrite it as the magnitude of the uh, gradient of the scalar function del phi grad phi, and then the magnitude of this differential element dr, and then cosine of the angle between them. So now you know what is this theta. Okay, like a dot b dot product of two vectors, when you write, you wrote it as a b cos theta. This theta is the angle between these two vectors a and b. Similarly here, theta represents the angle between this del phi vector and this dr vector, right? So if so the change d phi will be maximum. Okay, this d phi, the change will be maximum when this cos theta is 1 or theta is 0, right? So I will write d phi will be maximum when cos theta is 1, or we said theta is 0, right? So in other words, you can say this dr is the change in the position coordinates is along del phi. Okay, del phi is the vector. So if your dr, the change in the space coordinate, that vector is along del phi, then you will see that d phi will be maximum. So this we can say. So we can say del phi has the direction along which phi has the maximum rate of change. So that we also we can say, right? So I'm just rewriting, so I can say del phi here, that is grad phi, has the direction along which phi has the maximum rate of change, maximum rate of change. This is what we obtained, right? So we will write, otherwise, if you want to write what is the minimum change or no change, d phi is 0 when theta is equal to pi by 2. So cos theta, which is cos pi by 2, will be 0, right? So when this will happen, then we know that dot product, so you got the perpendicular, so dr, okay, dr is now perpendicular to what, this del phi operator, or you said the grad phi, okay, or del phi. So the value of phi here, okay, the value of phi remains constant as you move in a direction normal to del phi, because you got d phi is 0, right? So d phi is equal to 0, that means phi will be what, constant. So when phi will be constant, if you move, okay, if you move what, in the direction that is perpendicular to this del phi, right? If you are moving in a direction, if this dr is changed, you are moving that is perpendicular to this del phi, then what you will find, there will be no change in phi. So this is what we said. So the value of phi remains constant as one moves in a direction perpendicular or normal to del phi, right? In other words, you can also say del phi is normal to the surface of constant. So del phi, if this value del phi is always perpendicular to the surface of constant phi. That means if I am writing phi is equal to constant, I will start in the other way. Okay, so we said dr is perpendicular to del phi. For d phi is 0, so we got phi is constant, or in other words, you can say phi is constant, then del phi will always be what, del phi will be perpendicular to this phi is equal to constant surface, right? So this is very very important. Del phi is normal to the surface of constant phi, right? So this is what we if you understood, so we started with this d phi is equal to del phi dot dr, and we discussed the physical significance of this. So now if I will write any scalar function, right, any scalar function, and you can determine, you can easily determine what is the value of del phi from that. And once you got the value of del phi from that, you will be able to find out the perpendicular vector that is the vector that is perpendicular to the constant surface. So that can be easily determined. Okay, so in the next video we will do some numericals based on this, okay, this gradient of a scalar, and how to find out the vector that is perpendicular to a constant surface, or find the unit vector that is perpendicular to the constant surface, all that. So we will continue in the next video. Thank you for watching.